When we try to predict how sea level is going to change in the future, it's much more complicated because it really depends on processes that we don't understand very well, in particular the melting of these large polar ice sheets in Greenland and Antarctica. The Intergovernmental Panel on Climate Change, the IPCC, projects a sea level rise over the next 100 years of something like 20 to 40 centimeters. You can see this here in the context of the historical sea level rise. And one thing you notice right away is that the sea level rise measured from the TOPEX satellites is already at the very high end of what the IPCC projections are. Some people have criticized the IPCC for being a little bit too conservative. We'll take a look at this in a little bit more detail. A different view was put forth by Stefan Rahmstorf from Potsdam. What Stefan did was basically assume that the historical relationship between sea level rise and global temperature would remain constant. And so as temperature went up, he just used the same relationship to sea level, and he got a much larger sea level change, something like 40 centimeters to about a meter by the end of the century. So which of these is correct? The answer is we don't really know. The biggest uncertainty in all of this is not the thermal expansion of seawater. We know that the Earth is going to warm, although we don't know exactly by how much. But the big question is really how much ice is going to be lost from Greenland and how much ice is going to be lost from Antarctica. Those are the big factors that could change these calculations dramatically. If we look at the rate of mass loss in Greenland, we know currently that Greenland is losing ice mass. The way we know this is actually from a satellite called GRACE that measures the gravitational field of the Earth. This is a picture from GRACE that shows the changes in the gravitational field over Greenland over a period of about 5 years. And you can see that there's a big mass loss centered over southern Greenland connected with the loss of ice. Now, if you calculate how much that mass loss actually is, it's roughly 250 cubic kilometers per year. That sounds like a lot of ice, but actually, relative to all of Greenland, it's a pretty small amount. It raises sea level only about 0.5 millimeter a year. So it's really only about 15% of what TOPEX measures for the global sea level rise. So 0.5 millimeter a year, that's only 5 centimeters over a century. That doesn't seem like much to worry about. 5 centimeters is just this much. So what's the big deal? Why are we so worried about sea level rise this century if the melting of Greenland is only 5 centimeters? The answer really is that we're worried about the acceleration of that process. We just don't understand how glaciers flow into the ocean and how these large ice sheets behave as the Earth warms well enough to predict what's actually going to happen. And we've actually seen some extraordinary changes in Greenland in particular. For example, we used to see melting in the summertime around Greenland, just around the very perimeter of Greenland. On the left, you see melting from 1992, and on the right, you see what the melt pattern looked like in 2002. And just a couple of years ago, the summer was so warm in Greenland that for just a few days in the middle of the summer, every place on Greenland was melting at the same time. Really an extraordinary occurrence, and that's not very common. And the question is, will that trend continue? We've also seen amazing things on the top of Greenland. For example, in the summer, it's quite common to form melt pools. We used to think that these melt pools would form in the summertime, and then suddenly the water would disappear into the ice sheet. So here is a photograph taken of a large melt pond as the water sank into the ice sheet. Remember that the ice sheet is about 3 kilometers thick in the middle of Greenland. Glaciologists used to think that this water would actually flow down into the ice sheet and refreeze as it went, and so it would never make it to the base of the ice sheet. But in fact, now we know that there are certain pathways to get this water all the way to the base, and that this may actually lubricate the base. And what this does is allows the glacier to flow a little more easily and perhaps allow it to shed ice into the ocean a little more quickly. When we look at the GRACE data, we actually begin to see a little signs of acceleration of Greenland ice loss. You can see that there's just a little bit of curvature in the GRACE data. I think it's too early to tell whether this represents a substantial trend towards accelerating ice loss, but it is interesting that it appears to show a slight acceleration. We just don't know whether this is a long-term trend or whether this is going to continue. In Antarctica, it looked, for the first few years of the GRACE data, like the mass loss from Antarctica was pretty small. But again, it's shown some acceleration in recent years. And so what you see again is since 2002, from 2002 to 2004 or 5, there was a very slight decline in Antarctic ice mass. But from 2005 to 2009, there was a much steeper decline. And the question is that going to continue in the years ahead? If we look at the IPCC projections, we see that they were a little bit conservative in how they thought about sea level rise. In the gray fields, what you see is the sea level projections for 2100 for each of the different emission scenarios, ranging from the B1 scenario, that is the most dramatic climate change mitigation, where the countries of the world reduce their fossil fuel emissions dramatically, all the way to the A1F1 scenario, where most of the countries in the world continue to use fossil fuels and continue to emit greenhouse gases very aggressively. You can see that the range isn't that great in these different scenarios. It's about 20 to 40 centimeters, maybe a little bit higher in the highest emission scenarios, as much as 55 or 60 centimeters in the very high end. But what's interesting is that most of this contribution you see from these red crosses, though that's the thermal expansion of sea level. So the vast majority of the sea level rise that the IPCC looked at was from the thermal expansion of seawater. If you look at the contributions from the Greenland ice sheet or from Antarctica, you can see that in the case of Antarctica, they thought that Antarctica would actually increase in mass and cause a sea level drop. So they actually calculate a negative sea level contribution. This is actually directly in conflict with the GRACE satellite data. In the case of Greenland, what they did was assume in all of these scenarios that Greenland would contribute 5 centimeters over the century. That's essentially the same as what GRACE was saying for Greenland about 5 or 6 years ago. It's since accelerated a little bit. It's actually probably more like 8 centimeters if you average the current rate over the century. The IPCC makes this clear in their figure caption in the fine print, where they say the projected sea level rise assumes that the part of the present-day ice sheet mass imbalance that is due to recent ice flow acceleration, that is the ice loss from Greenland and Antarctica, will persist unchanged. It does not include the contribution from scaled-up ice sheet discharge, which is an alternative possibility. Can you assume that the current rate of melting of Greenland and Antarctica will continue unchanged for the next 100 years as the Earth warms? It seems like a very dangerous assumption to make. If Greenland and Antarctica were to melt a little bit faster, you'd probably end up in the middle of the Ramsdorf field instead of within the IPCC projections. There's one other wild card associated with sea level rise that really falls well outside of any of the projections, and that's because we really don't know how to evaluate the probability of this occurring. This is the large collapse of ice from East and West Antarctica associated with the loss of one of the large ice shelves. This is a picture of the Ross Ice Shelf. It's an enormous piece of floating ice, and remember, it's floating, and that means that 90% of it is actually below sea level. The Ross Ice Shelf is located on the Ross Sea, covering a good part of the Ross Sea. It's essentially land ice that has drifted out over the ocean and is now floating over seawater. But unlike sea ice, which is very thin, maybe just a few meters at most, the Ross Ice Shelf averages about 1,500 meters thick. So this is an enormous piece of ice. Because it's floating in the ocean, breaking off of a large ice shelf isn't actually going to change sea level directly. We've actually seen ice shelves along the Antarctic Peninsula break off. In particular, the Larsen B ice shelf was very dramatic as it happened over just a period of a few days. But when a big ice shelf like that breaks off, it doesn't cause sea level to rise directly because it's already floating on the ocean. It's already displacing seawater. The reason that the breakup of a large ice shelf is important is because it actually allows for the rapid flow of ice from Antarctica into the ocean. The way you can think about it is that these large ice shelves, both the Ross Ice Shelf over the Ross Sea and the Ronne Ice Shelf just across the way next to the Antarctic Peninsula, what they're doing is they're actually acting like the buttresses in a cathedral. They're actually holding back the large ice sheets that are sitting on land. In the case of East and West Antarctica, there are very fast ice streams that are supplying ice into the Ross Ice Shelf. If you were to break off the entire Ross Ice Shelf and have it disintegrate and float out into the ocean, what would happen is, essentially it's like pulling the cork out of the bottle. Suddenly, huge amounts of ice would flow into the Ross Sea and leave as icebergs. And you could imagine a very large amount of ice being discharged over a very short amount of time. Instead of a very slow sea level rise of maybe a few centimeters over a century, you could actually see a meter of ice loss or maybe even more from Antarctica in 100 years. And remember that there's over 50 meters of sea level equivalent stored in Antarctica total. So this is actually just a tiny fragment of what's possible in the centuries to come. One of the points here is that we actually don't really know how to evaluate the possibility of this happening. Scientists tend to be very conservative. So when we talk about something like the collapse of the Ross Ice Shelf, we like to use statistics. We like to try to use data and estimate the probability of something like this happening. But we've never seen anything like this before. And our models aren't nearly good enough to explain exactly how this might occur. Worse than that, we actually don't even have very good observations of the Ross Ice Shelf. Some of our best observations of what's happening underneath the Ross Ice Shelf actually come from thermometers strapped to seals that very clever biologists have used to try to understand the conditions in which these animals live. Now that's a little bit funny, but it's actually a little sad in that our observing systems are so bad that we're really flying blind in this one. If the Ross Ice Shelf were actually breaking up today, it's not clear that we would know about it. In general, we tend to ignore or at least de-emphasize these very uncertain situations, like the breakup of the Ross Ice Shelf. I'm not trying to suggest that the Ross Ice Shelf is certain to break up. It's going to break up at some point as the Earth warms, but I certainly don't expect it to happen in the next 100 years. The point is that I really have no idea, nor does anyone else, when it's going to collapse. We often treat these sorts of possibilities as high consequence, low probability events. In fact, they're really unknown probability events. We just have no idea whether they're going to occur or not. And the difference is actually very important. We tend to assume that they're low probability, and therefore, even though they're very high consequence, we don't have to worry about them very much. But in fact, they might be already fated to happen. In fact, they may be happening right now. We just don't know. This just emphasizes how much we don't understand about the climate system and how it's going to respond as the Earth warms. It's possible that the ice shelf will stay there for many centuries and that Antarctica will still be stable for thousands and thousands of years. But it's also possible that the acceleration of ice loss will be dramatic and that the Ross Ice Shelf might break off starting tomorrow and we could see a dramatic acceleration of ice discharge. We just don't know. One thing we can say for sure is that the scale of these ice sheets are so massive that it's hard to imagine any way that we could engineer to actually stop the collapse of the West Antarctic ice sheet or the East Antarctic ice sheet if the Ross Ice Shelf did break away. We're tinkering with processes at a scale that's enormous, and it's hard to imagine how we could put all these pieces back together if something did start to go awry. This is a picture of Hurricane Katrina. Really a beautiful storm. It formed as a much smaller hurricane and entered the Gulf of Mexico. And as it passed through what's called the loop current, which is a very large body of very warm water that extends quite deep in the Gulf of Mexico, it became a Category 5 hurricane as it moved across the Gulf and weakened just a little bit before it made landfall in Mississippi. It's often mistakenly thought that it actually hit New Orleans. Lucky for us, it actually missed New Orleans. There were roughly 400,000 people in the broader metropolitan area of New Orleans when Hurricane Katrina came ashore in Mississippi. If Katrina had actually hit New Orleans directly, we would have seen a storm surge probably 20 feet or so, and that would have just completely overwhelmed the city's defenses. We would have flooded New Orleans instantly, could have lost 100,000 people. Instead, what happened was that many of the dikes and levees around New Orleans were damaged as the storm approached, and the city flooded over a period of about 24 hours. We lost about 3,000 people. Now that's tragic, but really just a tiny fraction of what could have happened if it had made a direct hit on the city. Soon after Hurricane Katrina hit Mississippi, a paper was published in Nature by my colleague Kerry Emanuel at MIT. And what he showed was that there seemed to be a relationship between the energy dissipation by tropical cyclones and the sea surface temperature. Here is his graph for the Atlantic. In the solid line, what you see is the sea surface temperature from a region of the subtropical Atlantic where hurricanes form. And in the dashed line, it's Kerry Emanuel's power dissipation index, which is a measure not just of the number of storms, but also their power, how large they are, how high their winds are, and of course also how long they last. All of these things put together and integrated over each year allowed Kerry to calculate this power dissipation index. What you see is that since the 1970s, there's just a remarkable correlation between the hurricane power dissipation index and the sea surface temperature in the Atlantic. And this is very suggestive that hurricanes will be affected by a rise in sea surface temperature as the Earth slowly warms. The data before 1970 are not very reliable because we didn't have satellite observations of hurricanes, so we probably missed a lot of big storms. There's still a big argument about whether climate change will affect hurricanes in a way that we'll notice. The reason is that the power dissipation index is not exactly representative of how much human society will be affected by hurricanes. Most hurricanes that occur in the Atlantic never make landfall. They stay out in the ocean and dissipate their energy without having really any impact on humans whatsoever, unless you happen to be unlucky and get caught out at sea in the middle of one. What human society really cares about is large hurricanes that actually make landfall. And there, even relatively small hurricanes can have a devastating impact. For example, Superstorm Sandy, which was really a late season hurricane that merged with a different weather front and formed this enormous storm that made landfall in New Jersey just at the end of 2012. This was a relatively small hurricane, and yet it had a devastating impact of the people of the New York City metropolitan area. Part of the reason was that it was a very large storm, and so it affected a huge area. Because of its large size, it actually swept along a lot of the ocean water and created enormous storm surge and created flooding that was unlike anything that people in the region had seen before. Now, after every large hurricane, there's a debate in the press about whether hurricanes are actually caused by climate change. In the case of Sandy, it was particularly poignant because Sandy occurred just a few days before the presidential election in 2012. Indeed, Mayor Bloomberg came out and endorsed President Obama just a few days after Hurricane Sandy, specifically because of President Obama's climate change policies. So you could argue that Hurricane Sandy had a pretty large effect on the presidential election. Whenever there's a big storm, there's an argument about, is it actually caused by climate change? And the strict answer is, of course, no. Hurricanes have been around for a long time, as have floods and droughts and other types of extreme weather. And so no individual weather event can be directly attributed to climate change. But in fact, the story with Sandy is a little bit more complicated. Let's take a look at some of the possible ways that climate change might affect a storm like Sandy. Now, Hurricane Sandy occurred in late October, and like many hurricanes, it moved from the Caribbean up, passing Florida and the Carolinas, and moved up the east coast of the U.S. As it did this in late October, you would expect the hurricane to weaken enormously because by late October, the water in the western side of the Atlantic has actually gotten quite cold off of New Jersey. There's not a lot of swimmers at the beach in late October on the Jersey shore. But if you actually look at the sea surface temperatures off the east coast of the US in late October of 2012, what you see is that the temperatures were 4 or 5 degrees warmer than average. And in fact, Hurricane Sandy, as it moved from the Carolinas towards New Jersey, actually strengthened instead of weakened. And that was very unusual. So that is one way that a warming Earth's surface, that is, the warmer sea surface temperatures observed off the east coast of the US, would directly affect the intensity of the hurricane. Another effect is a little bit more speculative and is still being examined by scientists. This has to do with the funny path that Hurricane Sandy took as it came ashore in New Jersey. Most hurricanes make a sweeping arc. They form out in the Atlantic and move westward across the tropical Atlantic towards the Caribbean, and then take a turn and slowly move north and then ultimately move northeast, back out towards Greenland and towards Europe. In fact, most hurricanes never even make landfall and actually stay out at sea and become extratropical storms that might affect the British Isles. But Hurricane Sandy took a different path. It took the same turn that most hurricanes do and slowly traveled past the Carolinas and up the coast, but when it got to Maryland and New Jersey, it started to take a left turn and actually came ashore heading westward around New Jersey. This is very unusual. There are very few storms that have followed this path over the last 40 years or so that we have good satellite observations of hurricanes. One hypothesis is that changes in sea ice in the Arctic have led to a weather pattern where a high-pressure system up near Greenland is actually steering storms to turn towards the coast of the US. If this is correct, it's actually very significant because instead of large tropical storms moving out to sea, they might actually come ashore. What matters far more than how big the hurricanes are is what fraction of them actually make landfall. And if this weather pattern persists and more hurricanes start to turn westward and actually make land, the East Coast could be in big trouble.